All right, so we're going to talk about radicals and rational exponents for this section on 10.1 and 10.2. I'm also going to do a little bit of 10.3 at the end, but I did not assign any kind of work for that. All right, just so that you have seen it for when you move on into your next course. So first of all, when we talk about radicals or roots, all right, there's all different kinds of roots. Most one that we've worked with so far is a square root. So if I have something like this, 3 times 3 equals 9, all right, how I can undo that is, notice there's 2 of them, so that's 2. That's what a square root is. There's a 2 there that is not showing. So it's kind of undoing that square root. So I know that 3 times 3 is equal to 9. It's a square root, so that answer is going to be 3, because 3 times 3 equals 9, and it takes 2 of them to bring one out. So what I mean by that, let's say I have 2 times 2 times 2 is 8. Well, what if I then ask, that would be the cubed root of 8. Well, what number times itself 3 times equals 8? Well, that is 2 times 2 times 2. So because this is a cubed instead of a squared, it's 3. It takes 3 of these to bring out to be 2. All right, so let's see, how about, we're going to keep going off of here now. So what if I have the square root of 25? Square means 2, right? So that's going to be, what 2 numbers times itself equals 25? Well, 5 times 5. So it takes 2 of these to bring it out. So then the answer here is just 5. Okay, and we're going to do a little bit more on these breaking down perfect squares. So I'm not done with this. We're going to come back to it. Here's just a couple more, and then we'll move on to the rational. We'll come back here. So 144. A lot of your calculators can do this, honestly, and a lot of this you would do with your calculators, but you need to just understand the process of what it is. So this is the same thing as 12 times 12. And so that's going to equal 12. Okay, what if I have a negative on the outside? Well, that has nothing to do with what goes on underneath the radical or the root. So all I do is just bring that negative over. So we have a negative, and again, this is 12 times 12. Bring the negative over, negative 12. Now don't confuse that with this. Okay, so I want to think about that. What 2 numbers multiplied together equals a negative 144? Well, here I could say, all right, would it be 12 times 12? No. Okay, or could it be a negative 12 times a negative 12? Well, a negative times negative is positive. So both of these are going to give you a positive 144. So there's no way that we can get a negative when it's a square root. We could not get a negative underneath that. So that just means there's no real number for this. And eventually you'll learn how we'll talk about complex numbers, which are a way to start solving this type of a problem. And we'll do that in our next course. So what about though, what if I had this? Let's say I do the cube root again of negative 8. So you can't automatically look and go, oh, it's a negative, it's not a real number, because this is now a cubed root. That means it takes 3 numbers. So if it's a cubed root, is that possible? Negative times a negative times a negative is going to be a negative. So that answer is a negative 2. And that works because it's a cubed root instead of a square root. So just as a hint, anytime you have an even root, whether it's a 2, a 4, a 6, 8, whatever it is, you're not going to be able to get a negative. But if you have an odd root, like 3, 5, 7, there's a chance that you could have a negative answer for that. All right, so keep those straight in your mind. Sometimes you can do negatives under a radical. If it's an odd root, you can. Okay, what about a fraction? So if I have something like 4/9. Well, those are both perfect squares. This is a square root. It can be written, it doesn't have to be, but just so you recognize, these are the same thing. It can be written either way. So square root of 4 would be 2 times 2, and the square root of 9, 3 times 3, so 2/3. Okay, what about the square root of 13? Well, that's not a perfect square. So that's called an irrational number because it's not a perfect square. So if I put it in the calculator, then it's going to go on infinitely without repeating. That's an irrational number, okay? But I can find an approximation by putting that into a calculator. So if I want to put that, I'll just bring Desmos up here. Let's see where I have it right here. So if we want to look at the square root of 13, we just go down here to the square root 13. And it's approximately, I'll write this on the notes here, 3.61. We'll round it to 2 decimal places to the hundredths place. All right, so you can get an answer. It's just not an exact answer. So you notice how that decimal goes on infinitely? That's what's called an irrational number. So if we have something that is a perfect square or a perfect root, whether it's a cubed root, whatever it is, so this has an answer of 8. So that's going to be rational because it has an exact answer, 8. It's not a decimal, so that's rational. And then like we talked about before, what if I have the square root of negative 25? Well, you can't do that, right? Because it's a square, just like this one we did up here, the negative 144. That won't work. So that is just not a real number. All right. So just again, if I want to use the calculator, and let's just do, how about I want to know the fourth root of 2. Okay, fourth root of 2. Well, I don't know that in my head, right? We don't know what the fourth root is. So if we go back to our calculator, and I'm showing you this on Desmos because you all can use Desmos online. This is where you find that at down here at the bottom. If you go to functions over here and you go over to this miscellaneous, here is that, this is where you can put in different roots besides the square root. So see, it shows me what root do I want? Well, I want the fourth root of 2. So that's where you can do that. And it's approximately, if we round it to 2 decimal places, 1.19, an approximation. Okay, but notice it's irrational because that goes on infinitely. All right, so that's how you can do this on Desmos. Just go to functions, over to miscellaneous, and this one allows you to put in roots greater than 2. All right, so just to show you what a graph, actually maybe I'll just show you that on Desmos. So let's take a look and just see what a graph looks like for a square root. We're not really going to get into that right now, but just so you recognize, let's say I just wanted to do this, let's see here, square root. Let me see if I can do it this way. I'm gonna get out of here. That is the graph for the square root of x. That's what's called a parent function. It's what the original square root of x looks like. Now later, when we get into our next course, we'll translate that, we'll stretch it, we'll reflect it, and we'll do some different things with that, and we'll move it around. But that's just so you have an idea. And this just goes on infinitely, all right? That just goes on infinitely. So if we talked about a domain on that, like we did in our last lesson, the x values, would you agree that it starts at 0 with a bracket and then it goes to positive infinity? That's what's happening to my x values. And then for the range, where's the bottom of the y values? Well, it's also at 0. Right? And it also goes, my y values are increasing as this goes up and up and up and up. So it's also to positive infinity. All right, just so you know that I'm not going to ask you that right now, but just so you kind of recognize that and kind of know what the square root of a graph looks like. All right, so let's start talking about some rational exponents. Actually, you know what? Sorry, I'm going to I just changed my thoughts here. Let's go ahead and finish doing some of these, breaking some of these down, and then we'll go on to the rational exponents since we're kind of having this conversation. All right, so let's say we have something like the square root of 24. Okay, what we're going to do there is notice it's not a perfect square, but it can be simplified because there is a perfect square inside of that. So what I want to do is I want to break it down, and I'm looking for any two numbers that are the same, so I can bring them out, right? Two numbers that are the same, like this right here. So I can bring a 5 out. So when I look at this, now I see that I can break it down to 4 times 6. Well, we know the square root of 4 is 2 times 2. So I know that for this, I can bring a 2 out here to the outside. And 6 doesn't have a perfect square. It's 2 times 3. It doesn't have two of the same numbers multiplied to equal 6. So then I just have 2 radical 6. All right, now here's a second way if you want to break it down to primes. So primes, I can break it down and go, maybe I don't recognize that 4 as a perfect, or maybe I just thought, you know what, 3 times 8 equals 24. Okay, so this is prime, so I'm done with that. 2 times 4, and I'm just going to keep going because I'm not really thinking about, I'm just breaking it all the way down to prime. So this breaks down to 2 times 2 times 2 times 3, right? These primes right here. So remember, if it's a square root, that's 2, so it takes 2 numbers to bring 1 out. So this is still all under the radical. So I can bring a 2 out for that. And then I just have these, so I multiply them back together. So I have the 2 radical 2 times 3 is 6. So that's 2 different ways that you can work that out. If you don't see the perfect square in it, you can always break it down to primes. All right, so let's think about square root of 108. So I'm thinking about that, and I have no idea. I know it ends in an even number, so 2 will probably go into it. So I could use my calculator, but I'm just going to go ahead and do primes. So for me, let's do 108 here. I'll do it below it. I know that 2 goes into it 54 times. So that's a way to start. All right, so let's break 54 down. 6 times 9 is 54. Now, I do know that this is a perfect square. So I could stop there, but I'm going to keep going because I'm going to go ahead and just get all the primes. So 2 times 3, and then 9 is 3 times 3. So these are all broken down to prime numbers now. So what I have is I'm left with the square root. Let's see, I have a 2 and a 2 and 3 3s. That's what it breaks down to in prime. So because it's a square root, it takes 2. So I can bring a 2 out here. And I can also bring, I have 2 3s, I can also bring a 3 out. And so whatever you bring on the outside, you're going to multiply back together when you're done. So I can't bring any more out. So I'm left with this, so 6, and then I bring the 3 down. 6 radical 3. Okay. All right, let's just do some more here. So let's do the, how about cubed root? Let's do a 3. Cubed root is 16. So we want to find a number times itself 3 times. That goes into 16. So let's break it down. So I'm just going to break it down this way. So 8 times 2, right? Okay, so let's continue breaking that down. Instead of doing a prime tree, I'm just breaking it down this way. There's multiple ways to do it. How do I break 8 down? 4 times 2. Okay, now I can still break this 4 down. So 2 times 2, and then I still have a 2 and a 2. It's just doing the prime tree. I just didn't do it the tree way, I just did it this way. So these are all, which I should be putting, is a cubed root, not a square root. So a cubed root means we need 3 numbers now. So I have 3 2s that I can bring 1 out. So what I'm left with is this 2 on the outside, and whatever I'm left with under the radical, sometimes it's nothing. In this case, it's a 2. 2 radical 2. So if you just keep it simple like that, then it's not so bad. So let's look at a cubed root. How about a cubed root of 8? Now let's throw a variable in there, m to the 3rd. It's not any different than it is with your numbers. So let's take a look at this. We're going to do a cubed root. So 8 is 2 times 4, and then we have m to the 3rd. I'm going to break that down last. So we have a cubed root of 2, and then 4 is 2 times 2. So I'm just going to put 2 times 2. Now I have 3 m's. And you won't always have to write these out once you get that hang of what you're doing. But I just want you to see, because it's a cubed root, it takes 3 to bring out. So I can bring out a 2. And I can also, I have 3 m's, so I can bring an m out. So I brought a 2 and an m, and then there's nothing left underneath, so I'm done with 2m. All right, let's try another one. Let's do, how about, let's try 200, let's do k to this, let's do a couple here, r to the 8th. Let's try this. All right, so I need to break down 200. So 200 would be 100 times 2. Now I could keep going, but I know the square root of 100 is 10. So I'm going to stop there. Okay, but I could keep going and bring it out just like I did all the way down here. But to save time, I know that the square root of 100 is 10. If you don't, just break it down to 10 times 10, 2 times 5, 2 times 5. It'll work out the same way. Okay, now don't forget though, we still have 7 k's and 8 r's. So if I want to write those out individually, I can, if that makes it easier. But would you agree if I'm just going to show you over here, if I have k to the 7th, it takes 2 k's to bring one out because this is a square root. So if I have 7 and I take 2 out, right? If I subtract 2, then I'm at k to the 5th. And I've brought 1 k out. I'm going to put it down here. Because it takes 2 of them, right? And so now I have 5 left. Well, if I take 2 more out of there, I can bring another k out. And then I'm at k to the 3rd. Well, I can still take 2 more out of there. So I can take another one out. And then I'm just left with k. So that's what's left under the radical. All right, so here, actually, I think what I'll do, think this through a little bit. I think I'll put this down here. Let me come back to that. So we got the k. So this is what we're left with under the radical. All right, so let's look at the r. So I have 8 r's. So again, I need square root. If it was a cube root, I'd take 3 out. It's a square root, so I take 2 out. So 8 minus 2 minus 2. Oh my goodness here. 8 minus 2, so that's r to the 6th. So I've taken out an r. All right, I can take out another 2, and that gives me another r that I can take out. So now I'm at r to the 4th. Well, I can take out another 2 r's. That gives me another r. I'm at r2. Well, I can take out another 2. And then I don't have any r's left, right? So r to the 0, so they're gone. So they're gone. I don't have anything left under the radical for that. All right, so let's take a look back up here. So let's go ahead and simplify this. This is 10 times 10, right? So we'll bring a 10 out. So we're going to bring a 10 out here. We brought out 3 k's, and we had 1 k left. And we brought out all of our r to the 8ths. So what we're left with on the outside is a 10. We have 3 k's, so k to the 3rd. Just put them back together. 4 r's. And then underneath the radical, I got rid of that. We brought out a 10. So we're left with 2 and a k. A little more time consuming, but still the same thing. Now, if you don't like this, write them all out like that. You can certainly do that too, right? K 7 times r and take out 1 for every 2 of them that you have since it's a square root. Okay. Okay, how about this one? Let's do the 4th root of 32 y to the 9th. Okay, 4th root of 30. So we know it's going to be negative, and we'll just bring that around later to the outside. All right, so let's break down 32. We don't know what that is. So 4 times 8, 2 times 2. This breaks down to 2 times 4, and 2 times 2. So we're left with 1, 2, 3, 4, 5 2's under the radical. So I'm going to do this one the longer way that I told you you could do it either way. So I have 5 2's. Okay, now we have 9 y's, so I'm just going to write them out. Give myself writer's cramp. The only problem is when you get up to like 30, you're not going to want to write out 30. So what I would do is I would just take 4 out of that, 9 minus 4, right? And then 5 minus 4, like we did on the last one. But I'm just going to write this one all out the long way. All right, so I'm going to bring the negative down. Now it takes 4. So I'm going to bring that out. So I'm going to bring out a 2. It's just 1 2 for all 4 of them, right? All right, and then that one stays. And then here I have a y. There's 4 y's, so I can bring a y out. And then here's 4 more y's, so I can bring out another y. I'll just write those down here so you see what I'm doing. Bring out another y. And then what I'm left with underneath is a 2 and a y. I can't bring those out. So my answer, I multiply this together, so a negative 2 add 2y, so y squared, 2y. All right, now I want to show you just a couple things where this kind of gets into play, where you're going to see this. So if we have something like this, now we're going to multiply radicals. Okay, you can multiply any kind of radical as long as their root is the same. So their root must be the same. Otherwise you can't do it. All right, so this is going to equal 12 times 3, square root of 36. Well, what is the square root of 36? That's the same thing as 6 times 6, right? So that answer is 6, because it takes 2 to bring out because it's a square root. So I can simplify a multiplication problem as long as I know how to simplify radicals. Now sometimes, how about this one? How about square root of 5 times square root of 6? Well, they're same root, so square root of 30. Okay, now, sorry, my dog's coughing over there in the background. Okay, so now we got to break down. Can we break down 30? Does 30 have a perfect square? I'm trying to think in my head, I'm not sure. So 2 times 15, 3 times 5. So this breaks down to 2 times 3 times 5. So it doesn't have a perfect square because it doesn't have the same number twice. So I can just leave it as 30. So that's just my answer, square root of 30. It doesn't simplify any more than that. And that's an exact answer. If you want an approximation, you can put it in the calculator and round it. But it just depends on what. Usually we leave it as an exact answer. Okay. What if I have multiplying a variable? How about 20? Okay, we'll go 32 times t. Well, the radicals are the same, so I can multiply together. 32 times t is just 32t. Okay, now can I break 32 down? I think I can. So I'm just going to do it the shorter way. All right, so 32 is 16 times 2, and I know the square root of 16 is 4. So I can break this down to 16 times 2 times t, and I know this will come out to be a 4 because 4 times 4 is 16. If you wanted to continue this with the primes and get all the way down here, you'll get the same answer. It's fine. So 4, and then what's left underneath? A 2t. So you know how to reduce these down. You just got to be sure you get all the perfect squares out of them. Okay. Now, what if I have this one? What if I have the cubed root of 4 times square root of 6? What's that going to equal? Well, they're not the same root, right? This is a cubed root. This is a square root. So that we cannot do. That's just going to be, well, there's a solution. So we just can't do that because they have different roots. So you would just leave it like that. Okay, so last thing I want to talk about real quick is just a little bit of addition. Just so you've seen this, this is not on your final, nor is the multiplication. But I just want you to be sure that you have seen this. So if we have 4 radical 2 plus 3 radical 2. Okay, now we're not talking about multiplication, we're talking about addition. So when we talk about addition, then the root has to be, this number under the root has to be the same. Okay, so the number under the root must be the same. Okay, nice sloppy writing there. So these are the same. So this is just saying I have 4 radical 2's and I want to add 3 radical 2's. So how many total? 7 radical 2's. You just add these right here. Okay, so if I have 2 radical 3 minus 5 radical 3, I can do that because these radicals are the same. So 2 minus 5 is a negative 3 radical 5. Okay, now if I have something like this, 5 radical 2 plus 6 radical 3, can't do that. Not the same radical. Okay, so you can't do that. Now how about this one? Oh, running out of room there. Okay. So what I have to do is they're not the same radical, so I can't add them together now, but perhaps I could simplify them down and maybe 2 of them I could add together, maybe all 3 of them, I don't know. So you have to simplify this down first. So this one doesn't simplify, so I'm just going to leave that. So let's break down 20. So we can break that down to 4 times 5. And again, if you want to continue all the way down to the primes, but I'm going to stop there because I know the square root of 4 is 2. So I'm just going to go ahead and bring a 2 out for that. So I'm left with, I multiply it, right, times whatever's outside here. So we have 6 radical 5. Over here, we'll bring down our 2 radical 5 and our plus sign. All right, so let's break this one down. Let's see, we've got 45. How about 9 times 5? Again, you can continue to the primes, but I know that the square root of 9 is 3. So I'm just going to go ahead and stop there, just because I know that. So I bring a 3 out, multiply it times the 4 that was already out there, plus 12 radical 5. All right, so once they're simplified, notice they all have the same radical. So then I can add these together. All right, so 2 plus 6 is 8, plus 12, I have 20 radical 5s. All right, you guys, like I said, I am not going to put the multiplication and the addition on the final, but I want you to be sure that you've seen this and just it's familiar to you. All right, so that's all I have for you right now. So I hope you guys have a great week. Take care.